All right, let us begin. What we have today is the entropy and energetics mark scheme. The first few questions are pretty straightforward. They are mainly conceptual questions. So, first one was about state changes. State changes is particularly comfortable to answer once you are comfortable with it because all state changes follow the same pattern. So if you have trouble remembering that pattern, I would recommend looking in the Google Classroom. There is a handout for that. This is not. This is in contrast to chemical reactions, where a whole lot of other factors go into as what entropy at before and after. State changes are very, very straightforward in that way. Then we have question number 2. These are formulas to memorize. This is a little bit of a trick question in the sense that it combines two formulas. It's the one of them is and total entropy is equal to R ln K, and the other is total entropy is entropy of the system plus entropy of the surroundings. And then the entropy of the surroundings can also be broken down to the negative of the change in enthalpy over time. So it takes these equations and it kind of merges them all together into one resultant equation, and that one is A. So if you have trouble remembering them, I highly recommend writing out those three separate equations and kind of just, making yourself write them from memory until you don't make any mistakes. Question number 3 is another state change. Well, no, this one's not state change. This is dissolving, which is slightly different from state changes. That's worth taking note of. Here, they're trying to get you confused between the energetics of a reaction and the entropy of a reaction. Entropy just tells us whether a reaction can happen at all, and it also tells us whether this reaction has the ability to be a fully forward reaction or if it's like a reversible reaction. And if it is a reversible reaction, how much? By how much? Where is the position of equilibrium? What it cannot tell us is if that reaction is a fast reaction or a slow reaction. And in fact, it could even be a reaction that can only happen over the course of thousands of years even. That would still, if it's entropically feasible, it could happen. This part with the activation energy, this is referring to the energetics of the reaction, which is how quickly the reaction can happen. And the blue part here, this is the thermodynamics, this is the entropy of that reaction. Energetics is related to kinetics, whereas thermodynamics is related to entropy. So again, if you need further clarification on how to tell these two things apart, feel free to bring it up in one of our classes. I'll try to explain it again and maybe hash out something that can be used as a one-page reference. We'll see. It does kind of get into a little bit more advanced chemistry than A levels, but if they're going to make you do questions like this, then, it's worth understanding the difference between activation energy and entropic feasibility. Question number 4 is about comparing two different substances for which one has the most entropy. The way you would do that is you have to consider how many moving parts a particular pair of substances you're comparing could have. In the case of butane and 2-methylpropane, they have the same number of protons. They have the same number of electrons because their molecular formula is the same. So they have the same number of protons and electrons, which means that the movement of their electrons will mirror each other. Whatever the maximum number of different combinations of electrons that butane could have, methylpropane will also have. This is different from some other comparisons that are in this paper that we'll see later. The thing that is different are the ways the bonds are connected. And because butane is connected in one long chain, whereas methylpropane has like a little branch in the middle, the number of different ways the butane chains could arrange themselves in 3D space is way more than the number of different ways methylpropane could arrange itself. And that's why the entropy of butane is higher. Remember that standard molar entropy is an innate property. It isn't something that is kind of it's not calculated the way total entropy is calculated. It is an innate property of that substance in the same way that the weight of that substance or the color of that substance is an innate property of that substance. Only correct answer is A for number 5. This is about what substances can have 0 as its standard molar entropy. So 0 means that there is no alternative ways to arrange those particles at all. So in a perfect crystal, every single compound or ion in that crystal is locked in place. Or not even ions, like diamonds are very close to a perfect crystal. In a perfect crystal, the particles are locked in place. There's basically no alternative ways for them to arrange themselves, and that's why entropy is 0. Nothing in real life is actually a perfect crystal like that. Perfect crystals are an idea. They're not something you can actually achieve in real life. Then we have number 6, which is, they give you an equation. It is a chemical reaction, and they ask you which of these statements are true. These are a bunch of really good conceptual statements, so you could take note of all of them. Like, why is A incorrect, why is C incorrect, why is D incorrect? I'd recommend reading through them and just kind of making sure you understand each of these sentences to their maximum capacity. If you have questions about them, let me know. It's a pretty simple question otherwise. Number 7. Which of these changes has the largest increase in entropy of the system? Again, here we are mostly going off of state changes. So the one where we're producing a gas would be the one that's being favored, which there is only one of these reactions at all produces a gas. If there were 2 gases being produced, then there could be a little bit of ambiguity, and that would be a harder question. But when you have this question like the one in number 7, where only B produces a gas, that one's a very straightforward question answer. You pick the one that has something converting into a gas. 8 is lattice energy. So this question looks tricky because a lot of these sound plausible, which is why my recommendation for this, or rather the correct answer isn't something that sounds plausible until you really stop to think about it. It's not one of those questions where you immediately recognize the correct answer and you pick it, in my opinion. I would say that the easiest way to solve this question is to cross out all the other options. So B, C, and D are incorrect. I think it's easier to identify them as incorrect than necessarily A, some of the enthalpies of hydration of the gaseous ions, as the correct answer. But that is what A is. A is 2 different hydration enthalpies, one for lithium and one for chlorine, combined together because both lithium and chlorine, or rather, both the lithium ion and the chloride ion are hydrated in the same step and turn into AQ versions. Question number 9, the only correct answer is D. Here we have another one of those, like, comparing different entropies. This one, you are going to pick the one that has the greatest number of electrons, because electrons are, again, the mobile part of these sorts of substances, right? Entropy is to do with things that are able to move, and the probability of these movements taking up a lot of different patterns. The more patterns you could have in theory, the higher the entropy is. So here we have this sulfur dioxide. Compared to everything else, it is the largest atoms. Largest atoms means it has the most number of electrons. Having more electrons means it has more possible ways to position. If there were 2 that were similarly sized, then you would pick based on which of them has the more loose bonds, if you will, the bonds that can swing around the most, which was the case with the previous version of this question that we looked at. Question number 10, enthalpy change of solution here may be calculated using 3 pieces of data. Which of these pieces is not required? Again, I would recommend sketching out a energy cycle like this, and then you can use that to figure it out. So if you want to copy this, I think that would be a good idea. So the best, in my opinion, the most reliable way to solve these types of questions, a little bit of rough work. There is plenty of space in your question paper for rough work. Like compared to even my worksheets, the actual Edexcel papers will like dedicate half the paper, it feels like, to giving space for rough work. Question 11 is also something somewhat similar in that way. You should do your rough work. This is a entropy of system calculation. So entropy of system is always minus of the entropy of reactants plus entropy of products. So whatever the reactants are, add them all together and slap a minus on them, or you can negative them each individually like I have done here, and then add them to the total entropy of the product. Whatever number you get at the end, that is the answer. Number 12 is, once again, highest standard molar entropy. By now, it should be pretty easy to figure out how those things work. In this question, we can immediately eliminate copper and ethanol because copper is a solid and ethanol is a liquid. So yes, technically, ethanol has the most electrons, it has the most ways it can arrange its bonds, but because it is a liquid, we can eliminate it. So that leaves us with hydrogen and carbon. Between hydrogen and carbon, carbon has the most electrons. Number 13, entropy change. So this is a series of reactions and you have to work out total entropy. This is very, very simple. Only the ones with positive total entropies will be feasible. This is applying the formula, and they've done all the calculations for you. Number 14, again, it is a question about this time it's standard enthalpy. So for standard enthalpy, we want to look out for substances that are actually in their standard state. And then we apply whatever number of moles are required for that particular substance's definition. Again, I will be making a handout for all of the standard enthalpies that you have to deal with. So emphasis on memorizing all of the definitions. Definitions are very, very important. Then we have number 15A. So which of these would have the least exothermic lattice energy? So lattice energy is affected by the covalent character. So when you have large ions with small charges, so large ions being the negative side and small charges being the positive side, then you will have very low lattice energy. Lattice energy is higher when there is more of a harmony between the sizes and the charges. So for example, something you could use to help anchor yourself in this concept is that magnesium oxide has one of the highest lattice energies of any ionic compound because the magnesium and the oxygen ions are very, very similar in size to each other, and magnesium and oxygen are both +2, -2. They attract each other very strongly, and they don't polarize each other very much because they're similar in size. This statement here is worth memorizing. It's a bit more help in solving these types of questions. Then which of these compounds would be expected to have a large difference between their experimental and theoretical lattice energy? So having a large difference between what exists in reality, which is the experimental result, versus what should exist in a perfect theory, this difference is caused by ionic bond polarization. So again, review how polarization occurs. I have a handout. I don't remember if it's in the A2 Google Classroom or not. So I will go check that after done recording here, and I'll take a look and see if the handout is in the A2 Classroom. If not, expect for it to be uploaded in a few minutes. after this is done. Question number 16, standard enthalpy change of solution for potassium chloride is this, and the solubility is this. Which of these explains the solubility of potassium chloride in water? So, if something can happen, its entropy has to be positive, right? And here you have a bunch of statements that are wrong in all situations. So it's worth taking note of them as always incorrect. There is no situation where you have lattice energies that are exothermic, right? So that's just always the case. Or sorry, no, it is that in all situations lattice energy is always exothermic. So that's not unique to potassium chloride. If A was the explanation, then it would explain all substances, all ionic substances would dissolve in water. But that's not the case. All ionic substances don't dissolve in water because some of them are entropically unfeasible, even if their lattice energy is exothermic. And same thing for hydration. Hydration is also always exothermic. So if that was the explanation, it would make it, we would be living in a world where all ionic substances dissolve in water, which is not the case at all. Question number 17, the total entropy change is this much. Then what is the value of the equilibrium constant? This is an R ln K question. Remember, entropy total is R, which is the gas constant, times ln, the natural logarithm, times K, right? Which means ln K is total entropy divided by R, which means K is equal to e to the power of this division. You can do it in parts. You can do total entropy divided by R first, and then e to the power of that number, like e to the power of answer on your calculator. You get this number. This is a very common type of question you've probably have noticed after solving this paper, so it's worth being comfortable with this type of math. It's very simple. So moving on to section B. This question draws a lot of information from the data booklet, and what I noticed is this data booklet has a little bit of an annoying characteristic in the fact that half your data will be near the top of the data booklet, half your entropy data, and the other half of your entropy data will be at the bottom, at the very end of your data booklet. So I have kind of pulled out screenshots of where to find that information. You're looking for the column that has the S theta. Theta just means standard conditions. These are the standard entropies for a whole bunch of substances. Near the beginning of the data booklet, you have it for elements, and near the end of the data booklet, you have it for compounds. So for this first question, 18A, you need the compound entropies. You need the compound enthalpies. My bad. This is an enthalpy calculation, right? So we use these enthalpies to draw our Hess cycle, and then use our Hess cycle to work out our entropy, our missing enthalpy of reaction. Once we have the enthalpy of reaction, we can start working out the entropy of this reaction. So total entropy is system plus surrounding. This first question asks for the system entropy. System entropy is adding up all the reactants and making them a negative number, and then adding up all the products and adding that to that initial negative number. So in this reaction, we had, this is our only reactant. So we look for the entropy of that reactant. It's over here. This thing, the one marked in green. And then we put those numbers down. The products as well. The potassium iodide is right next to it. You take that and you put it down here. It's one of the products, so it's a positive number. And then oxygen is from the element section. So oxygen, there's 3 of them, because each of these oxygen entropies is for a single lone oxygen molecule. It is an oxygen atom. It is not for oxygen molecule. We 3x that. And that gives us our oxygen number. And then put those numbers together in your calculator, and that's your system entropy. Surroundings is the negative of the enthalpy of reaction divided by the temperature. Enthalpy of reaction is what we calculated in 18. Once again, if you have trouble doing these types of questions, make up a number. This part is fairly straightforward, so you can make up a number to get the marks here at least, even if you stumbled in this part. And there will always be error carried forward, so if you did your work but it was wrong, they would not double cut your marks. Remember this. Be careful about the units. Enthalpy is typically calculated in kilojoules, but entropy is calculated in joules. So we need to do a conversion here. That's why it's times 1000 over here. And then we also have to turn the sign negative. This enthalpy was a positive enthalpy. This reaction is an endothermic reaction. So when we come here, we're minusing that. So it's turning into a negative entropy divided by T. We are told that the entropy total has to be the lowest number you can get for that reaction to be able to occur, right? They want you to find the lowest temperature possible for this reaction to occur, for this reaction to be entropically feasible, not its activation energy. This is about entropic feasibility. Because it's an endothermic reaction, it is only feasible at high temperatures where enough energy from the surroundings is being added in. So we set our delta S total to 0 because 0 is the lowest entropy where a reaction is feasible. This is a reaction that is very, very reversible, but it's still going to go in the forward direction at least a little bit. So we have our total set to 0. It's system plus surroundings. We have our formula for surroundings. We already calculated the system entropy, so we just slap that in. Put in everything for surroundings except T, which is our unknown. We rearrange 2 negatives on either side. We can cancel them out. Then we have this number over T is equal to this number. So we move that to the other side. This number over this number. This gives us 661.5 Kelvin. And remember, because we cross the signs out, this is a positive number, which, I mean, that's kind of redundant. There's no such thing as negative Kelvin, but, you know, I would always recommend putting a sign down. Also, mind the rounding. Be careful about under and over rounding for these types of questions. This question is, again, conceptual, so worded in a more plain Englishy way would be that thermodynamic feasibility. So basically, this reaction is thermodynamically feasible, but it is extremely slow because it has a very high activation energy, meaning its reaction would take days, if not months, if not years, to actually get to a point where you're noticing that the reaction is occurring. It's very, very slow. But it is thermodynamically feasible, which means it's not impossible. An impossible reaction does not occur in any capacity. A high activation energy does occur, but very, very slowly at low temperature. Then moving on to B. Here, again, a bunch of lattice energy stuff. This part of the mark scheme can be a little bit intimidating to look at, but it's basically just giving you a bunch of different ways to arrange the formula that will give you the same results. You can try to pick this apart and assign marks for yourself, or I can just give you the marks when you bring in your paper for checking a second time by me. That part is whatever you prefer. Here I have a Hess cycle, so if you want, you can copy this down for your own reference as well. So I'm not going to dwell on this. This is like usual Hess cycle stuff. You can come back and take a look in the mark scheme. This is more. This is that same thing about how lattice energy is related to covalent character. In the simplest of terms, lattice energy increases when there is a small ionic radius and large ionic charge for both participants. This one is not, this second part here, ionic charge, is not relevant in this question because sodium and potassium are both +1, but it is relevant in other situations where you are comparing different charges, so I've included this in the criteria given here to be more generalized, all sorts of questions of this type. Moving on to 19, here we have a question about entropy, and the thing is, they're giving you a reaction that we know occurs. We are operating from the premise that this is a reaction that definitely occurs. So what can we say about it? We can say that the entropy is positive, and this reaction gives us enough information for us to be able to even predict or identify why entropy is positive. Entropy is positive because we are taking a solid and turning it into a pair of gases. That is always going to be a positive system. B is another reaction calculation. So again, system minus the system entropy is the negative of the reactants plus the product's entropy. So the simple math: turn all of your reactants negative, and then make your products positive. Add them together, and you're done. These are also numbers that I believe you have to pull out of the data booklet. Yes. So again, you'll find them near the end of the data booklet. They're all compounds. Here, calculating surroundings, be careful about the conversions. You have a minus in the formula, and the enthalpy has to be converted from kilojoule to joule. So this time the enthalpy was negative as well. It was minus 36. It's given in the question. So it's minus 36 times 1000 with the whole thing negatived and then divided by the temperature. And the temperature is also given in Celsius, so we need to convert that to Kelvin, which is plus 273. So all these numbers, chuck them in the calculator, and this is your final answer. Here, question number D, I've just circled the working because unlike a lot of other questions, this one at least does give you the working in something that is fairly easy to look and follow. Like, total is just adding all the numbers together, and that's your total entropy. Very simple. Question number 20. Here we're starting to get into the lattice enthalpy Born-Haber cycles. So Born-Haber cycles are lengthy, so take it very, very slowly. Remember, from one line to the next, you can only have one change. So but it can be any change. In this example, I did calcium solid to calcium gas as a first change. You could do chlorine molecule to chlorine atoms as your first change, the atomization of chlorine. That's absolutely fine. As long as every step is only one change, you can put whatever you want on the steps, as long as they're correct, the arrow direction is correct. So for example, delta H6 has to be the first E electron affinity of chlorine because it's a negative number, and that's the only downward arrow that you have to fill in. And they kind of like prime you to that as well by forcing the Ca2 plus and 2Cl minus here, so that should hopefully not be too difficult to notice that you have to put the electron affinity. But yeah, again, if you have trouble with this, come back to the mark scheme and look at all the numbers and everything here. I've labeled it step 1, 2, 3 as a recommendation for like what order you should be doing things in. So I think the most sensible way to do it is to first write the equation one step change at a time. So first calcium to gas, then a +1 calcium, then a +2 calcium, and then atomized chlorine, and then ionized chlorine, and then everything reacts together to make our calcium chloride. And then you put the numbers in, reading off the table, and then finally you pick your start, you pick your end. It'll be a line, right? This line is the starting line, and this line, ending line. So we are going down this way, up this way, and then all the way here, and then down again. This is our end. So a lot of numbers in this question. We'll see their signs flipped. This one sign flips, this one sign flips, this one sign does not flip, this one flips, this one flips, and this one flips. So I skipped writing the flipped signs just to save space because it was getting really cluttered. But if you are writing with pen and paper, you'll have more space to work with than me. You can also write the flipped signs and then just combine all the numbers into a single line and put that into your calculator. Always write more, so you have to think less. That's going to be consistently my advice for the entire time that you'll know me at A level. Write more to think less. This is the mark scheme of this. Again, you can try to parse exactly how the marking criteria is done. Read through this if you want, or you can leave it to me to assign the marks for you. Number B, this is about the difference between theoretical and experimental lattice energy. So we've talked about that. It's to do with covalent character. You can use this as a guide for how to like structure your answer, if you will. Explain questions care very much about having both the effect and the cause highlighted. So the effect is that there is covalent character in calcium chloride. And the cause is that calcium ions are very small. And then a final effect is that this leads to polarization. You have to make sure all your ideas are connected together really, really well in explain questions. Number C, this is about shows the theoretical lattice energy. So this is all theoretical. None of these are experimental, so covalent character does not come in at all. What is going on here? There are 3 lines that you have to connect together. So what I've done is I've underlined the bits that you should be writing and then helped with joining them together. So lattice enthalpy becomes less exothermic because the radius of the metal ions are increasing, which results in less attraction between ions. So, easy. You can even score all 3 marks in one line if you connect them all together like this. But I would recommend I always recommend splitting it up so you can keep track of how many points you've made, but that's up to you. Another Hesse cycle, again, a whole bunch of calculations. This is 21. Let's look at D first. So again, Hesse cycle, draw your cycle, label your start and end, and then plan your route around the cycle. Flip the signs of whatever arrow you're going against. Keep the sign the same for whatever arrow you're still going in the same direction as. All of that, and then punch the numbers into your calculator at the end. 21 is another entropy question. Here, they've just left you with a big blank space to fill in everything by yourself. So let's start with what they want. They want the entropy total, which is system plus surrounding. That part is pretty straightforward. What is entropy of system? The negative of the reactant plus the products, right? All of the reactants, negative, plus all of the products. So these are our reactants. I've put the negative signs here, but you could also add them all together and then give the negative sign at the end. It's up to you. And these are our products. Again, you can combine them all in one go like this, or you could do a second line to show the total reactant, show the total product, put the sign, appropriate sign for the reactant side, put the appropriate sign for the product side, then punch that into your calculator. There, this number. Then we have the surroundings, which is minus of the enthalpy over T. Again, enthalpy is in kilojoules. We need to convert to joules, so times 1000. It was a negative enthalpy, so we have to double negative it into a positive and then divide it by the temperature. Gives us this number, and then total is just adding these 2 numbers together. One of these numbers was negative, the other number is positive, but the overall entropy is positive, so this is a feasible reaction. Marking criteria is shown here. Try to figure it out for yourself, or you can leave it to me. Up to you. Here, I underline the stuff on this side because I think this is actually a better explanation than what they want in the marking criteria. But typically, the marking criteria makes sense, is going to be a more reliable answer. So I would recommend trying to learn these wordings as best you can and using the underlined stuff here as kind of explanations to help convert the more formal explanation into words that are easier to understand. So higher temperature would result in an insignificant change in entropy of surroundings because the entropy of surroundings is already quite large. And then the entropy of system is not really affected by temperature. So because the higher temperature is not being able to benefit the surrounding entropy because it's an exothermic reaction. That's why increasing temperature actually makes the entropy become slightly less feasible, but the numbers are such a big difference before that anyway. The system entropy was minuscule compared to the surrounding entropy. So it doesn't matter. In the end, the entropy total is becoming less feasible, but by a small amount. The reason we use this higher temperature, even though it's slightly worse entropically, is because it is helping the rate of reaction. So while the reaction is becoming a little less feasible, which means its position of equilibrium is a little less in the forward direction, the speed of this reaction is way faster, and that makes it a more beneficial process in an industrial. Here again, it's the R ln K equation, so memorize it, rearrange it, blah blah blah, nothing fancy. This one is another Hesse cycle. This one's easier than the previous one, honestly. Again, fill in the information, mark your start, mark your end. Conveniently, this one wants an enthalpy change that is so straightforward that none of the arrows have to change sign, so you don't have to do too much at all. If you have no trouble with the previous Born-Haber cycle, you shouldn't have trouble with this one. Then it's calculations from the Born-Haber cycle. Nothing too fancy here. Again, if you need help with figuring out the numbers, I can do that for the marking. Oh, I can do the marking part. That's fine. Again, question about enthalpy change. The question about theoretical versus experimental value. So we've talked about this a whole bunch. Read through this. If the number for the theoretical value and the experimental value are very similar, that means that there is little to no covalent character. If it's very different, that means that there is a lot of covalent character. This is a question about electron affinity. Electron affinity is easier when the atom is small, so the distance to the nucleus is less. So a chlorine has a easier time gaining an electron, right? Electron affinity means gaining electrons, right? Chlorines have an easier time gaining electrons than iodine because the chlorine nucleus is closer to the outer shell, so it's able to attract foreign electrons. How you could think about it, these are good guidance on how to word that in a formal way. 22 is, once more, entropy, surroundings. Very, very simple. Here's the math. Again, be able to get this by now, surely. B is a question about entropy theory again. Explain what can be deduced from your answer in A about the sign and value of the standard entropy of system. We calculated a negative entropy, right? Here it is minus 86.242 joule per Kelvin per mole. This is negative. The surroundings are losing entropy. This is an endothermic reaction. That means that the system entropy has to be positive. It has to be a positive number that is greater than the entropy lost surroundings from this being an endothermic reaction. Otherwise, this reaction is not entropically. Here, it's one of those big questions. These are always a pain to solve. What I've written here is some guidance on how you can start organizing your thoughts, because I feel like that's the thing that students like. You have all these ideas in your head, but how do you present that in the best structured way? Because this is very much a structure biased answer. You can't just leave a word salad in the answer. You will not get any marks for that. So I would recommend start by putting all of the relevant points in bullet points on your paper, just whatever comes to mind, and then using some sort of sign, like say ticks or circles or whatever, to split these bullet points into 2 paragraphs. So based on themes, 2 paragraphs. So for example, this question is about comparing sodium chloride to magnesium iodide. So you could split it down the theme of the positive ions and the negative ions and explaining that. Try to always break down your bullet points into 2 separate themes that you can categorize them into. If you are feeling confident, you could do 3 as well, but 2 minimum, and then write them down into those paragraphs. And that should generally help you with catching all of the marking points as well as getting the full marks for this question. Moreover, I would recommend, if you left this blank or if you did a lesser job of this the first time around, I highly recommend using these as those bullet points I just mentioned, and then organizing these into 2 separate paragraphs and writing it out as practice, and then using that practice write-up as your reference for explanations related to theoretical and experimental lattice energy differences. Very, very complete picture of how that ends up being the case. Section C we're starting with some more calculations. Really, these questions all come from different papers, but really for entropy and energetics, there's not a whole lot of variety, which is, I suppose, a good thing. A lot of these questions are very similar. We have system entropy, which is negative of the reactants plus the products, same old, same old. Here is a question about much more theory-driven, entropy-related topics, right? This is about using ideas about disorder, which is what they're saying is using ideas about disorder means ideas about entropy. Explain whether the sign of your answer is as expected. So your answer should be yes, because we are talking about a feasible reaction. We're not talking about something that cannot happen. Because the number of ways of distributing energy quanta, again, this is very physicsy, but what it's saying is the ways to distribute the particles, and these particles contain energy through their movement, through their electrons and all that. The number of ways to arrange the mobile parts of this substance has increased when it goes from N2 and H2 into NH3. Chemicals that have fewer mobile parts have less entropy. Nitrogen and hydrogen separately have more mobile parts than ammonia, right? So that's all there is to it. Here we have, again, the formulas. It's surrounding. Same thing. Be careful about the conversions. Fine. System entropy, very easy. It's this time they gave you the total entropy, so you're just going to rearrange the formula. You take total on this side minus the surroundings, and that's the cool. Another one of those structured questions. These the positions of these reflects how I found them in question paper. So yeah, one of these big structured questions was in section B in a paper, and the other one was in section C. I don't really know what the rhyme or reason to that is, but it is what it is. This is again a good piece of write-up to use for this time the question is about entropy. To explain one advantage and one disadvantage of a higher temperature. Here I've also done something where I've connected these bullet points together with like joining sentences. So if you needed a little bit more guidance on how to organize your paragraphs, you could use that as inspiration. So rate of reaction is higher at higher temperatures. Therefore, more ammonia would be produced in a given time. This makes the temperature of the at higher temperatures, this would make the entropy of the surroundings less positive because the sorry, this shouldn't be because, it should be as a result, the entropy total would be more negative. Right? So this results in this point. It shouldn't be because, it should be as a result. The other relevant point is that Kp is going to decrease. The position of equilibrium is going to shift towards the reactants. But that's okay, because the position of equilibrium is, while the position of equilibrium is moving left and it's giving lower yield, it is still producing more ammonia in a single second than it did before. So there's this last point can actually connect back to the first few points. So again, remember, we want to rearrange these bullet points into paragraphs. Don't just spit them out in this exact order. Actually think about what order we can give this information out in that will organize them into two discrete paragraphs. That would be my tip for this type of question. And we are almost at the end here. Question number 25. Yep, this is the last one. One final system and total and surroundings, and that's it. Math, hopefully by now that doesn't cause any kind of issues. So with that, we are done, and hopefully this helps with the questions. If you have any of these that you would like re-explained in class, always bring it up. No, that's totally fine, and I'll check this as well to precise feedback on the topic.